Okay, let's get started. Are we recording? Yep. Okay, let's get started. Hopefully everybody survived the, yeah, oh.
Can I see this little QR code?
The code.
I couldn't think of the word.
Hopefully everybody survived. I'm sure was a exciting and hectic weekend and whatnot. So with everything that happened, but congratulations, I guess, are in order. Okay, so today we are entering the third dimension, and that's what we're going to be doing today and Wednesday, is looking at how to take what we've done over the past few lectures and extend it into 3D. Now, I want to say a quick note on the homework. So homework 2.3 and 2.4 are being graded. One of the things my TAs noticed was that it seems that there are a couple of people that are still might have the wrong textbook, because they were going through the submissions, and there were a few where, I mean, it looked like they knew what they were doing, they were just doing the wrong problem. So what I would suggest is that you just go to Microsoft Teams, because I had posted the homeworks up until, I think, the one that was last Friday, and check those problems versus the ones that you've been doing, and if they match, then you're using the right one. If not, you might need to exchange your textbook and whatnot. What I will do is I will grade those assignments, those standing assignments, on their merits. So it might take me a little while, but from here on out, if it's the wrong problem, I'll probably just have to say it's the wrong problem and give a 0 and move on. Okay, homework 2.5 is due today. I think that's probably one of the more challenging assignments that we've had all semester, especially with those pulleys. But I think 2.6 and 2.7, while maybe a little longer, are going to be a lot more straightforward. And so with that, I want to get started. I do want to make sure that everybody's clear on the schedule. So today we are doing 3D vectors, so describing vectors in 3 dimensions, and then we're going to do 3D equilibrium. So lecture 9 and lecture 10 are going to be our remaining lectures that focus on stuff that'll be covered on exam 1. On Friday, we're going to cover cross products. Cross products will not show up on exam 1, but I want to give a buffer to turn in homework 7, and I want to start talking about rigid body behavior, which is what's going to be focused on exam 2. I'm going to assign a homework assignment on cross products, but it will not be due until after the first exam. It won't be due until the 23rd. And it's a really short assignment, so I wanted to try and make that easy as possible. Next Monday, we're going to come in and review for the first exam, and then we celebrate on Wednesday. So I wanted to make sure that everybody's clear on the schedule. So, sound good? All right. Okay. I don't like being that professor who comes in and says, oh, you have a test on Wednesday. What? So I want to make sure that you're aware of what's going on. Okay. So today what we're going to do is we're going to describe vectors in 3 dimensions, and what that's going to involve is a more explicit use of unit vectors, something that we kind of danced around a little bit in our previous calculations, but we haven't quite really addressed. And then I also want to talk about orientation in 3D, so angles and directional cosines. Okay. Now, to be clear, I want to make sure that we understand how things are going in 2 dimensions. Oh, sorry, I hit the button. I want to make sure everybody understands what's going on in 2 dimensions. So what we're doing is we're summing vectors in 2D, and so our equations of static equilibrium say that the sum of those vectors must be equal to 0, right? Now, if we split this up in IJ notation, we're going to have the sum of forces in the x direction times I, plus the sum of the forces in the y direction times j, but those sums must be equal to 0. So we're left with 2 equations and ultimately 2 unknowns, which is a simultaneous system that we can handle pretty easily. So all we're going to be doing in 3D is we're going to have a simultaneous system of 3 equations and 3 unknowns. Now, make sure that you don't forget the acceleration due to Earth's gravity, and don't forget basically we're just adding vectors up in 2D by just adding up those individual components, which is basically this is what we're going to be doing today, just in 3D. Now, so let's talk about the third dimension. So all we're doing here to incorporate the z-axis is just adding another term, and you're going to find that it's not just the definition of our vectors that's pretty straightforward, but also all of the operations that we need to do. So finding the magnitude, the equation of equilibrium, you're going to find that all that stuff has very striking similarities to what we did in 2D. So what we've got is we got the sum of the force in the x direction times the I vector, the y direction times the force in the y direction times the j vector, and now we have a new magnitude of the force in the z direction times the k vector. So as I and j were unit vectors, so remember, what's a unit vector? A unit vector is a vector with a magnitude of 1. So we have I and j, which are unit vectors with a magnitude of 1 in the x and y direction, respectively. The k vector is just a vector with a magnitude of 1 along the z direction. So again, we're just going to be doing the same thing, it's just a little bit more. Okay? So this slide, I would argue this slide is one of the most important slides for this whole unit of the class. I haven't touched on this yet, which I'm going to do a little bit later. But if you look at this, there are very striking similarities between 2 dimensions and 3 dimensions. So how about vector description? So we have a pile of junk times I plus a pile of junk times j. We just had the same thing, just a pile of junk times k. Okay? What about the magnitude of a vector? How do we find the magnitude of a vector that's expressed in ij notation in 2D? We just use Pythagorean theorem. The square root of the x component squared plus the y component squared. We just do the same thing in 3D. We just have another component. So it's the x component squared plus the y component squared plus the z component squared, and we take the square root of the whole thing. All right. What about vector addition? Well, we have all the x components times I plus the y components times j. Just another term, just the z components times k. It's just more. Okay. What about the equations in static equilibrium? Well, we have 2 equations of static equilibrium in 2D, 3 in 3D. Okay. Now, what does get a little different is expressing orientations in 3D. We do it a little bit differently, but it's actually a lot more systematic. It's really, really, it's easier than you would think. But I don't want to information overload you. We'll do more on that later. Now, I want to recall the definition of a unit vector, and before I get into this, I kind of want to pull up the calculations from last time, because I want to just highlight something real quick, and I want to highlight, where's my pen? I want to highlight this computation that we did in the last example. Okay, so let me refresh your memory. So this is our previous example, and we had this boat that was being dragged along a river, and we had a series of cables holding it in place. And I want to look at cable AB. Okay, now AB had a magnitude of 40 pounds, and it was oriented in this fashion. So the first thing that we had done is we computed all of our angles, and then I want to look at this computation. So we had the vector equals a pile of junk times I plus a pile of junk times j. Now what went inside each of these coefficients? Well, we had the magnitude of the vector times the cosine. The magnitude of the vector times the sine. So this part right here, okay? Now let's follow it through on the next line. So what happened on the next line? So we had a magnitude times the cosine plus a magnitude times the sine. Now I want to pay attention to this line right here. Could I have factored out the 40 pounds? I mean, I could have, right? Make sense? Okay, now, that's my first question. Here's my second question. This vector AB, what is the magnitude of that vector? It's 40 pounds, right? That's the magnitude of the vector. If I were to factor out that 40 pounds over here, what am I left with? I'm left with a vector that has a magnitude of 1, right? Make sense? So I propose that a way of expressing vectors is to factor out the magnitude and sort of separate our magnitude and direction, okay? We had talked about this a little bit last time, and we used this expression to sort of serve as the basis for defining ijk. So remember, what is a vector? A vector is a mathematical object that defines a magnitude and a direction. I can factor out that magnitude, and I'm left with this, a vector which has a magnitude of 1 and some given orientation. And so any vector that has a length of 1 is termed a unit vector. I, j, k, those are separately each unit vectors. So what we're going to do in 3 dimensions is we're going to use this notation much more explicitly. Okay? What we're going to say is that when we have a vector in 3 dimensions, we're going to explicitly separate out the magnitude and the direction. So we're going to have the magnitude of that vector, which we might call f, and then the unit vector is going to be the vector that expresses direction, and we're going to term that lambda. So if you're wondering what that little symbol is, that's the lowercase Greek letter lambda. So we're going to have a lambda component times x plus a lambda component times y, or lambda component of x times I, lambda component of y times j, etc. The reason that we're expressing it this way is because we kind of need to have a vector that solely expresses direction, because when we look at the problems that we're dealing with, it's going to be easier dealing with these separately in order to find the orientation in 3 dimensions. That's probably the hardest part of 3D, is just figuring out these unit vectors. And honestly, if you can plot points, x comma y comma z, then I say the hardest part, but that's pretty much all there is to it. So let me show you how that works. And there's a lot of formulas here on this slide, but don't worry, we're going to have a lot of practice doing it. So this lambda vector here is the direction of the force in question. The way that we determine that direction is we're going to actually use the line along which it acts. So let's say I've got some force here out in space, and I know it acts along this line mn. So how do I determine that force vector? How do I actually define that force vector? Well, the way that I define that force vector is I say I'm going to have force times lambda. Let's talk about lambda. Okay? Lambda is a unit vector in this direction. Well, let's see. This is a line out in space. So if I know the coordinates of this point and the coordinates of this point, I can actually find that vector pretty easily. So the first thing that I do is I determine the coordinates of this point here and this point here, and then I take the difference between those coordinates to get how much we go in the x direction, how much we go in the y direction, how much we go in the z direction. So essentially what I'm defining first is a distance vector from point A to point B. Then what I do is I take that distance vector, so we'll call that, I'm just using the term mn right here because I'm going from point M to point N. What I do is I've got that vector, I get the length of that vector. How do I get the length of a vector in 3D? I just use the Pythagorean theorem. I take that vector and I divide it by its own length. What do I get when I divide that vector by its own length? I get a vector with a magnitude of 1, okay? So I get the distance vector, turn it into a unit vector, take that unit vector, multiply by the force vector, boom. Then it becomes the same problem that we've been dealing with this whole time. So what we're going to be doing today is just that very aspect, only describing the vectors in 3D. We're not going to worry about 3D equilibrium until Wednesday, because I want you to get some practice doing this. Now, the one thing that maybe is a little different other than that is the orientation. So sometimes we're also interested in not just the magnitude of the resultant, but the direction of the resultant, right? So remember, we did this in 2D. I had a bunch of vectors added up at one point. I wanted to determine the magnitude of the result and the direction of the resultant. Now, in 2 dimensions, that was pretty easy. I just have a vector. What's the angle? But in 3D, I want sort of a systematic way of handling that. And so it's actually really, really easy. Okay? Now, what we can do to determine those orientations is sort of look at like this term, this image right here, and I kind of want to focus on this, because if you understand this, you'll understand what's going on right here. Okay, so let's look at this. Let's say I have a vector, and that vector has a length of 1. So if I were to take a ruler and measure this, that length is 1. How do I determine that angle? Well, I believe that the cosine of that angle is the adjacent over the hypotenuse. And the hypotenuse in this case is 1. So would you agree that if this length is 1, that this length is in fact the cosine? Would you agree with that? So I also propose that this length right here, this cosine of x, equals this right here. Because here's the vector, right? Here's my unit vector with the length of 1. This right here is how much of that vector acts along the x-axis. This is how much of that vector acts along the y. This is how much of that vector acts along the z. So if I have this vector here, if I'm just looking at 2 dimensions, this is how much of that vector acts along the x-axis. So the cool thing is, if you want to determine the orientation of a vector in 3D, all you have to do is get this lambda vector here, and then take each of these terms, take the inverse cosine, and boom. You know how many degrees it's off the x-axis, how many degrees it's off the y, how many degrees it's off the z. It's actually much easier, I think, in 3 dimensions than it was in 2 dimensions. And I know I'm probably throwing a lot of formulas and equations at you. Once we start getting into the thick of doing this, these calculations, I think you'll find this is pretty straightforward. And I think that the way 3D works, the best way of actually understanding it is to just do some damn problems. So let's do some problems. So I have a 3D vector example problem that's honestly going to take us the rest of class because I really want to take our time with it and make sure that we understand it. Okay, so I have here this wall, and there's all sorts of dimensions and whatnot, and it's being held in place by the cables that are shown right here. Okay, now what I'm focusing on right now is this point here, this point A. Now I propose that there are 2 forces being applied at A. There's a force in this direction and a force in this direction. Now I've got all my dimensions here, and I've got the magnitude of each of these 2 forces. What I want is the resultant of forces acting along this point right here, and specifically magnitude and direction. So we're not solving a 3x3 system of equations to determine unknowns. Right now we've just got 2 vectors at a point, and we're just adding them up. That's all we're doing. Okay. So we're taking it slow, but again, I think you're going to find that this is not hard. The problem is maybe just a little bit longer than it normally would be. So let me escape out of this. Let me go to my example here. Now let's take a look at this. Okay. So I'll give everybody a sec to sort of like catch up on this. But what we've got going on here is we've got our point A right here. So if we wanted to look at this from a free body diagram perspective, I've got a force like this, and I've got a force, I don't know, maybe like that. So we'll call this T, I can do better than that. We'll call this TAC and TAB. That's about the best you're going to get out of me in sort of a 3-dimensional view, as it were. Okay. Now, in order to define these vectors, what we're going to need to do is we're going to need to establish some coordinate system. Okay. Now, I'll tell you that. Go away, Siri. I know. I'll tell you that when we start doing homeworks and exam problems, more often than not, I will define that coordinate system for you, simply because I don't want 17 different ways of doing the problem and they're all the correct answer, or they're all correct approaches. I want a singular coordinate system such that we're all doing the problem the same way. So what I'm going to do is I'm going to go ahead and define a coordinate system. And the way I'm going to do that, and it doesn't really matter where I place my origin, but what matters most is the orientation. So what I'm going to do is I'm going to say that, we'll say that this is the x-axis. We'll say that this is the y-axis. So you can sort of see, like, imagine if you were standing on the edge of the wall and looking, so x is this way, y is this way. And we'll say that z acts sort of along the wall. Okay? So that's sort of how we'll go about defining this coordinate system. Like I said, I think my main point for doing this, at least for this example, is that, in the real world, you're not going to be given a scenario where your boss, your client says, here's the coordinate system. You're going to need to define it yourself. And so I just wanted to go through that exercise for us just to know that you kind of needed to do that here. One thing I will say is that later on, dealing with things in 3 dimensions, we're going to get a lot more experience doing stuff like this and employing things like the right-hand rule. For now, I'm easing you into it. Later on, we'll definitely get heavier into doing a lot of this work ourselves. Okay. So what we've got to do is the first thing that we need to do is define what are called distance vectors, okay? I would argue this is, at least for right now, the hardest part of the whole problem, okay? So we're going to have a vector AB and a vector AC. Okay? Now that vector is going to be something times I plus something times J plus, now we've got a new term, something times K. And the same thing here. Okay? Now, keep in mind, we're focused on point A, so let's deal with AB first. Okay? We have a tension in cable AB. So what that means is, if this is point A right here, then that force is going to be applied like that. Okay? That's tension AB. Okay? I mean, in other words, think, if this cable is holding this wall up, what's happening to this pin? That cable is wanting to yank on that pin like this. Does that make sense? Okay. All right, so let's deal with AB first. Okay. Now, the way that we do this is we just follow our coordinate systems one by one, and let's determine our components. Let's start off with the x-axis. So the x-axis goes sort of outside the wall. So if here's the wall, like if this right here is the wall, the x-axis is pointing like this. So if I'm at point A, how far do I have to go along the x-axis to get to point B? 16 feet. Does everybody see that? Now, here's the question. Is that positive or negative? Negative, right? Because the x-axis is pointing this way. Ooh, that orientation's bad. I think I can do better than that. I think the x-axis probably points more like that. That's better. Okay. So the x-axis is pointing this way, but to go from A to B, I'm going this way. Okay. So that means that this value here is negative 16 feet. Is everybody okay with that? That's probably one of the most important things to understand right now. Everybody okay with that? So somebody else tell me, what's this component right here in the y direction? To go from A to B, how far do I go in the y direction? Positive 8 feet. Does everybody see that? Okay, so we're going positive 8 feet. Now, how about the z direction? Say it again. 11 feet. That's exactly right. That's where this term right here comes into play. Bringing out those ENGR 102 skills or CE 102 skills, those dimensions in 2D and 3D. Does that make sense? Okay, if that makes sense, somebody help me out. AC, what's this term right here? So keep in mind, AC, we're talking about this vector right there. Talking about that vector. So along the x-axis, what's this? Negative 16 feet. What about this? 8 feet. Positive 8 feet. So far, it's the same. But, I mean, it can't be exactly the same because they're literally pointing in two different directions. Well, that's where this value comes into play. If this is 11, what's this? Sorry, say it again. Negative 16, not positive 16, negative 16. Because to go from A to Z, we're going 16 feet, but we're going in the other direction. And where do we get 16 feet? The whole wall is 27 feet long, and from A to B is 11, so A to C's got to be 16. Make sense? So this is our AC vector. Scroll down a little bit. I want to stop for a second and see if anybody has any questions. Is that good? If that's good, then I promise you the rest of this example is probably going to feel pretty rote and pretty mechanical, which is a good thing because that means it's not very difficult. All right? Now, these vectors are expressing distance. Okay, what's their units? Their units are feet, right? That's great, but that doesn't help me in the land of static equilibrium or in statics in general. I need vectors that are expressing quantities in forces. I need pounds. I need to know the tension in cable AB. Well, I don't have that now, so how do I get that? Well, let's start here. This is vector. So let's look at vector AB. Bless you. So this is a vector expressing the distance from A to B. Why don't I start off by trying to find the magnitude of these vectors? Let's start with that. Let's get the magnitude of these vectors. Let's start with that one. So how do we get that? Well, we have negative 16 feet squared plus 8 feet squared plus 11 feet squared. And we take the square root of all of that. What do we get for that? And I'll say this. If you think that I'm being a little overboard by writing feet every time, trust me, there is a reason for it, okay? Be wordy with your units. Trust me, it will reduce errors later. I'll go ahead and tell you, this comes out as a nice, pretty number. 21 feet. I think I heard multiple people say that, so I think I got seconds on that, okay? Now let's do the next one. So it's all going to be the same. Except for that z vector, or that z component. So what do we get for that? 24 feet. Do I have a second? Okay. Now, my reasoning for computing that is because now I want to get unit vectors. Okay? So let's get unit vectors now. Now, the way that you compute a unit vector is you take a vector and you divide it by its own magnitude. Okay? All right, so let's start off with AB. Okay? So the way that we're going to do that is we're going to take vector AB and divide it by its magnitude. So what is that term for term? So we're taking negative 16, 8, and 11 and dividing it by 21. This one right here? Tell you, I don't think I can zoom it, but I will.
And above it, where you have it right beside unit vector.
Oh, I'll tell you what, I'll write it bigger. I'll write it bigger. Is that better? Okay, and I'll make this a little bigger. Again, don't hesitate to tell me this stuff. If it's too small, tell me. Is that good right there? Okay. So what we're going to have here is we're going to have each of these components. It's a vector, so we're going to have I plus j plus k, each of those multiplied by some component. Only now it's going to be a fraction, okay? And so what were the components? They were negative 16 feet, 8 feet, and 11 feet. But the bottom is going to be 21 feet, 21 feet, 21 feet. Okay? Now, for me, I'm going to leave this in fractions. I'm just going to leave it in fractional form because I think that's easier. But what happens to the units? They cancel, okay? The point I'm making is, so what are the units of a unit vector? There are none. It's just a unitless quantity. It is a vector that's only purpose is to express direction. So it should not have any units, okay? So this is negative 16 over 21 times I plus 8 over 21 times j plus 11 over 21 times k. Now, same thing with vector AC. So we have negative 16 feet, 8 feet, and negative 16 feet. I can do better than that. Only now the magnitude is 24 feet. Okay? So now these fractions will simplify a little bit. Like 8 over 24, that's 1/3. 16 over 24, that's 2/3. So now I've got negative 2/3 times I plus 1/3 times j plus negative 2/3 times k. And again, are these vectors with a magnitude of 1? Well, I think we can spot check that. Let's look at this vector right here. Okay, so what's 2/3 squared? 4/9, right? So 4/9, 1/9, 4/9, 4/9, 1/9, and 4/9 adds up to 9/9 or 1. So the magnitude is 1, right? So the cool thing about these vectors is that they only express direction but contain no magnitude. So if I want force vectors, all I need to do is multiply these by the respective force magnitudes, and boom, there we go. So So to determine a force vector, we just take the magnitude times the unit vector. Now we were given the magnitude of the forces in the beginning of the problem. So TAB equals, anybody have that written down? 840. And TAC is what? 1200. So, therefore, if I wanted to describe this vector, I would take the magnitude times the unit vector. Okay, and so what do we get? We get 840 pounds times, and then it's negative 16 over 21 times I plus 8 over 21 times j plus 11 over 21 times k. Let's handle each of these components one at a time. So So what's the x component? Anybody got an answer for me on that? What do we have for this x component? So what's 840 times this fraction? Negative 640. Do I have a second? See, I brought my Casio FX 115 ES Plus, so that's all I'm saying. All right. So 8 over 21 times 840, I think that's going to be half of that, so that's 320. All right, and what about the last one? What's that one? Somebody over here. Say it again. Do I have a second? All right, that's exactly right. And notice the magnitude. So take a look at what we've got here. We have a vector describing a force in 3 dimensions in terms of pounds. Does this process kind of make sense in order to describe vectors in 3D? We start off by describing the distance vector, convert that into a unit vector, and then multiply it by the magnitude of the force to get the force vector. That makes sense? Everything else is the same as what we did before. So TAC is, again, we take that times its unit vector, magnitude times direction, essentially. So that's negative 2/3 I. I think I can do this one in my head because I've got 1,200 times 2/3 and 1/3. So I know 1/3 of 1,200 is 400. So that makes that 800. So this is, what is that? Negative 800 pounds, positive 400 pounds, negative 800 pounds. Did I do that right? All right. I want to stop and take a second. Does this make sense? Okay, so if I want to determine, so let's go back to the beginning of the problem. What are we doing in this problem? In this problem, we have this spike in the ground at point A, and there are 2 forces being applied at point A. Here are those 2 forces expressed in IJK notation in 3D. If I want to determine the resultant of those 2 forces on that point, what do I do to those 2 vectors? Add them boys up. That's correct. That is what we will do. I didn't say it. All right. So resultant of, I'll just say resultant. Okay. And so the way that we compute a resultant is we sum our individual vectors. Okay. So I'll rewrite these again. So actually, you know what? I'm going to be lazy. Oh, not what I meant to do. Hold on, let's try this. Okay, never mind. OneNote doesn't like me. Let's just rewrite them. That's what I get for being lazy. that. Okay. And so all we're going to do is we're just going to sum those up like we, would, any vector. So R is the sum of these vectors. And so we just add up each of the components. So we have a component times I. What do we have? We have negative 640 plus negative 800. So that's what? Negative 1440 plus, okay, what about J? 320 and 400 makes 720. Plus, and here we've got 440, but then negative 800. So what is that? Negative 360? Did I do that right? Okay. Let me do something real quick. I'm gonna sort of divide these into sections so that when you review these later, you'll kind of see what we're doing from section to section. Okay. Okay. So now here's our vector in 3 dimensions. Now, if I'm designing this spoke or this system to hold this wall up, this is great, but maybe I just like to know the magnitude of force on that vector, or on that spoke. I just want to know the magnitude. I mean, this is the magnitude along the x-axis, this along the y, this along the z, but I want to know the magnitude of the whole thing. So if I wanted to determine the magnitude of the entire vector, how would I do that? I'd use Pythagorean theorem. I just add another term, okay? So we'll say magnitude of the resultant and so the magnitude of the resultant, I'm going to give myself a little bit of room here. It's not that hard. I'm just going to scroll down a bit. So we can say R, or the magnitude of the R vector, is just, let's just do this. So negative 1440 pounds squared plus 720 pounds squared plus negative 360 pounds squared, that. And so what is the magnitude of that vector? I'll tell you, it's not a pretty number. It doesn't come out pretty. We'll say 2 decimal places. 1649.73 pounds. Do I have a second? Boom. So that's how much force is being applied at that point to keep that wall upright. Now that's the magnitude, but that's not the direction, okay? So in order to determine the direction, it's a little bit of a 2-step process. So let me show you how we're going to do that. So the first thing that we're going to do, so direction So the first thing that we're going to do is we're going to determine a unit vector for the resultant. Now, how am I going to do that? How do I determine a unit vector? I take the vector and do what to it? Divide it by its own magnitude. So I take R, that is odd, R, and I divide it by its own magnitude. So what I've got is negative 1440 pounds divided by 1649.73 times I plus 720 over 1649.73 pounds times J plus negative 360 over 1649.73 times K. Okay? And I'll go ahead and do this one for you because these numbers, we're getting close to the end of class time. These numbers are not going to be pretty. More often than not in real world engineering applications, they're not nice, pretty numbers like 2/3 and 8/11. They're kind of messy. So I'm going to write them out like this. Now I'm going to use a high number of decimal places. The only reason I'm doing this is just to make sure that you're able to follow along the calculations with me. I'd probably personally only go to about 3, but you'll see why. So I've got negative 0.8728 here. This next term I've got positive 0.4364. And this last term I've got negative 0.2182. I kind of like to go to 3 or 4 decimal places on this, especially with the 3D equilibrium, because I think it leads to a little bit more exact answers, but I don't like to go any more than that. Now, if you use the Pythagorean theorem on these 3 numbers, you'll get an answer of 1, barring some rounding and whatnot. So this is the direction of that vector in 3D, okay? But here's the thing. I propose that each of these terms, okay, I also propose that lambda r, that, not b, r, is the cosine of that angle about the x-axis times I, plus the cosine of that angle from the y-axis times j, plus cosine theta z times k. In other words, so let's do one of these, and I think it'll be easier to explain. So if I want to determine, let's say, theta x, what I do is I take the cosine inverse of negative 0.8728. Okay, and when I do that, I'm going to get something like 150.79 degrees. Likewise for the other ones, this one I get 64.112. And this one, I get 102.60 degrees. So like, for example, if I look at, let's say, the y-axis, if I want to know where the resultant is, I point along the y-axis and I rotate 64.12 degrees, and that'll get me to that vector. So from each of these axes, so from the x-axis, if I point to the x-axis and rotate 150.79 degrees, if from the y-axis I rotate 64.12 degrees, from the z-axis 102.6 degrees, I will arrive at where my resultant is pointing. And those angles, you start at the axis in question and you rotate counterclockwise, just like you would in polar coordinates. So if I have polar coordinates, that's 0 degrees, and then I rotate up. I rotate counterclockwise, just like with all of these. So if this is the magnitude, this is the direction. Does this make sense? All right, if this makes sense, we're going to do a 3D equilibrium problem on Wednesday, and that's going to be it for what's on your first exam. I'm going to stop the recording and pull the QR code back up for those of you that didn't get a chance to catch it, but that's all I got. I will see you all on Wednesday.